Section: Introduction. In this section, we discuss the importance of updating large language models, LLMs, to ensure they remain accurate, safe, and ethical after deployment. It is crucial to efficiently update LLMs to protect privacy, eliminate bias, and incorporate new information. One common method is fine-tuning the model on new datasets, but this can lead to overfitting and forgetting important knowledge. Various research approaches have been proposed to address these challenges, such as training external memory models or hyper-network models alongside the LLM. However, these methods face scalability issues and can slow down the editing process. Updating large language models in real-world settings is hindered by the complexity of fact editing and selective fact forgetting. In contrast, humans can quickly update their knowledge, which is believed to rely on the hippocampus for rapid learning. Inspired by this, we introduce Larimar, a class of LLMs enhanced with an external episodic memory controller. Larimar follows the idea of complementary learning systems, where a fast learning system, hippocampus, records episodic memories, and a slow learning system, LLM, learns from these memories. The episodic memory module stores factual updates and guides the LLM decoder. We aim to efficiently update this memory as new information arrives, using a hierarchical memory framework similar to the Canova machine. By coupling the memory to the LLM through end-to-end gradient descent, Larimar can quickly adapt to new knowledge during inference. We introduce training-free selective fact forgetting and information leakage prevention operations based on Larimar's memory updating mechanism. Our approach enables fast and accurate adaptation of LLMs to new inputs, outperforming baseline methods in knowledge editing and input context length generalization tasks. Section Summary. In this section, we introduce the concept of updating large language models, LLMs, to ensure they remain factually accurate, safe, and ethical post-deployment. Efficient mechanisms are crucial for quick updates to protect privacy, eliminate bias, and incorporate new information. Inspired by brain learning mechanisms, we propose Larimar, an LLM augmented with an external episodic memory controller, enabling fast and accurate adaptation to new knowledge without the need for extensive training or fact tracing within the model. Section: Model Architecture. In this section, we define our model architecture and notation. We have input and output spaces denoted as X and Y, respectively. Our model consists of an encoder E, X, to R, C, and a decoder D, R, C to Y, connected through an adaptive memory. The encoder produces outputs in a latent space of dimension C. The memory has K rows to store encoded episodes of length N, with an initial state M_0 in R, K times C, and updates through reading and writing weights W_0 in R, N times K, resulting in an updated memory M. During training, our goal is to maximize the conditional log likelihood of lane P, X, vert M, where X is an exchangeable episode consisting of N samples. We optimize a variational lower bound of this conditional likelihood, similar to variational autoencoders. This helps the model compress X into a memory M, which then acts as a distributed associative memory. In practice, we learn M on a noisy version of the latent encodings Z plus Xi, where Z equals E, X, for an episode. The memory is updated using a reading weight matrix, W, which is a random variable ensuring the generative ability of the model. The memory readouts are obtained as Z_readout equals WM. The model's architecture involves jointly training and optimizing the encoder, E, associative memory, M, and decoder, D, for an episode, X, using a specific loss function. After training M_0 through backpropagation, the posterior memory, M, is updated efficiently in one shot by solving a minimization problem. This problem involves minimizing Z_zeta W_0 M, which can be solved by computing matrix pseudo-inverses. For our implementation, we used a BERT large encoder combined with either a GPT-2 large or a GPT-J6B decoder and a memory matrix, 512 by 768, for training experiments. We named the resulting models Larimar 1.3b and Larimar 6b. In testing, the Larimar 1.3b model achieved a perplexity of 14.6, while the Larimar 6b model reached 15.9 on 1,000 random Wikitext samples, showing that adding memory has minimal impact on performance. We also discuss memory operations, including write-in, read-out, and generate operations, which manipulate the Z encodings. Sequential writing and forgetting involve updating the memory matrix and key covariance matrix to add new encodings or forget previously written ones. This process ensures that the memory remains the least squares solution for the growing sequence of data. The weights can be computed based on the current memory or a fixed reference memory used during inference. Section Summary. In this section, we introduce a model architecture consisting of an encoder, decoder, and adaptive memory for memory-augmented learning. The model is trained to compress input episodes into a memory space and optimize a variational lower bound to maximize conditional log likelihood. Memory operations such as write, read, and generate are performed efficiently using matrix pseudo-inverses, enabling sequential writing and forgetting of encoded data in the memory matrix. Section: Scope Detector. In this section, we utilize a scope detection mechanism to determine if the incoming query aligns closely with the information stored in the memory, similar to Serac. If the query matches the stored facts, we pass the corresponding memory readout to the decoder for memory-based decoding. Otherwise, the query undergoes unconditioned decoding. We explore two scenarios: external encoding-based scope detector, ESD, and internal encoding-based scope detector, ISD. In ESD, we use mini-LM to estimate embeddings from 1.1b sentence pairs, with a 384-dimensional output space. The ESD stores encoded facts as vectors in its scope storage. During testing, we calculate the one nearest neighbor cosine similarity for an encoded input sentence to determine the detection score. For multi-sentence inputs, we process each sentence separately and consider the maximum similarity. The ESD model achieves a detection equal error rate of 2.9% and an F1 score of 0.974 on 3,800 samples from the Easy Edit dataset. In ISD, we employ the Larimar encoder E to embed counter-fact samples. These encodings train a binary scope classifier using positive samples from rephrased original facts and negative samples from neighboring facts. For Wikibio generation, we concatenate sequences of k+1 consecutive sentences from Wikibio entries into Larimar memory. The first k sentences serve as a prompt for reading the memory and generating a response text R. We experiment with fixed and variable length sequences, such as 1, 1, 2, 1, and j, 1 pairs. We aim to assess Larimar's ability to produce valid biography text, with a low perplexity value denoted as text PPL, R, indicating coherence. By fine-tuning GPT-2XL on Wikibio and an open web text subset, we observe improved perplexity values for biography text generation. In our evaluations, we find that Larimar can fully generate the next sentence in more than half of the inputs for shorter input pairs. However, as the input length increases, Larimar tends to generate empty responses more frequently. Additionally, we compare Larimar's editing speed with existing baselines, demonstrating its efficiency in editing tasks. Furthermore, we evaluate Larimar's performance on the counterfact dataset and ZSRE benchmark, showcasing its effectiveness in editing and maintaining neighborhood specificity across different decoding models. Section Summary. In this section, we introduce a scope detector mechanism to determine if incoming queries align with stored facts for memory conditional decoding. We explore two scenarios: an external encoding-based scope detector, ESD, using mini-LM embeddings, and an internal encoding-based scope detector, ISD, with Larimar encoder for counterfact samples. Additionally, we evaluate Larimar's performance in generating valid biography text and its efficiency in editing tasks, showcasing its speed advantage over existing LLM baselines like Rome and Grace. Section: Sequential Fact Editing. In this section, we assessed Larimar's ability to perform sequential editing by adapting it to a setup that addresses the challenge of forgetting previous edits after multiple sequential edits. We incorporated a method introduced by Hartvigsen et al. That utilizes a pre-trained language model, GPT-2XL, to update a codebook of edit key value pairs, demonstrating memory retention during sequential edits. Our evaluation involved selecting a subset of 200 facts with 5 rephrasings each from the ZSRE validation dataset for testing. In Larimar, each sequential edit involves updating the global memory without the need for gradient-based updates on incoming edits. For every edit, we write the encoding of the rephrased query combined with the corresponding answer to memory. We compared Larimar's performance to Grace using the edit retention rate, ER, which measures the mean F1 score after 1,000 sequential edits when querying the memory with the encoded query for each written fact. Larimar does not undergo fine-tuning on question-answer data. Instead, we treat each question-answer pair as a fact in memory and query the memory with the original question. Additionally, we evaluated Larimar's ability to generalize to rephrased prompts and compared it to Grace using different datasets. Our analysis showed that Larimar achieved comparable ER performance to Grace while maintaining its original test set performance. Larimar 1.3b also exhibited editing speeds approximately 10 times faster than Grace on GPT-2XL. Furthermore, we explored Larimar's capability for selective forgetting, where we investigated if a specific fact can be selectively erased from a set of facts stored in Larimar's memory. Our results demonstrated Larimar's ability to compress more than the memory size limit of facts into its memory, outperforming some baselines but falling short compared to others. Larimar showed promise in selectively forgetting specified facts during inference while retaining other knowledge, showcasing its memory updating mechanism's effectiveness. Section Summary. In this section, we evaluated Larimar's ability to perform sequential editing by integrating an adapter to update a codebook of edit key value pairs with a pre-trained language model, GPT-2XL, demonstrating memory retention during sequential edits. We assessed Larimar's performance using the edit retention rate, ER, and compared it to Grace, showing comparable performance while maintaining its original test set performance and achieving faster editing speeds. Additionally, we tested Larimar's ability to selectively forget specified facts during inference, showcasing its capability to selectively erase specific facts while retaining the remaining knowledge, outperforming baselines like MEND and Rome in memory compression and recall tasks. Section: Generalization to long input context. In this section, we explore the generalization to long input context. We conduct fact recall with extended context using information not present in the base decoder's pre-training data. To achieve this, we gathered facts from CNN Fast Facts spanning 2021 to 2023. The input text is divided into chunks, denoted as T, within the range of Larimar's training context window. Each chunk is stored in a separate memory m_i equals 1, T. When given a query, we access and read from each of these memories. The readouts from these memories serve as the foundation for the subsequent memory, which is then queried and read from again. This process continues until the number of readouts in the final memory aligns with Larimar's input training context window. This recursive exploration in the latent memory space, utilizing readouts to construct new higher-level memory, enables us to handle long contexts with Larimar's memory trained on a relatively short episode length. The retrieved information from the final successor memory, denoted as Z_R, is fed to the decoder to predict the response. It's important to note that a memory hierarchy, also observed in the hippocampus, is believed to play a role in learning. Our experiments demonstrate that Larimar's recall performance remains stable even with increasing input context length, outperforming some competitive baseline LLMs trained with longer training contexts. We also compare with the supersizing transformer, a memory-augmented model, which did not exhibit competitive recall performance as it was not trained for memory condition generation. Larimar's memory processing in the latent space proves to be efficient in terms of the number of KV cache token computations compared to baseline methods. In a scenario with 128 facts, Larimar requires an average time of 0.36 s to read from memory, whereas the Mistral 7B base model takes 1.44 s. Learning to copy from the context is crucial for Transformer's language modeling capabilities. LLMs with non-attention-based architectures often fall short compared to transformers, partly due to their inability to copy from the context and generalize to longer contexts. This has spurred research on hybrid architectures. Our findings suggest that combining a hierarchical memory model with a generative pre-trained transformer, as seen in Larimar, could be a promising approach. The end-to-end training of the fixed-size latent memory with the decoder in Larimar introduces an explicit state to the decoder, aiding in controlling the decoding process and enabling accurate copying from the context in a generalized manner. Memory control also facilitates real-time knowledge editing and prevents information leakage. By attending to the memory readout during decoding, Larimar uses O1 memory to predict each token, offering memory and computational advantages. This approach helps in mitigating hallucination in wiki bio generation. By generating wiki bio entries through recursive prompting after Larimar memory writes of token chunk pairs and concatenating the outputs, we observe perplexity values for the generated wikibios. The Jaccard index analysis reveals that for a sweet spot interval of k values between 6 and 12, Larimar effectively mitigates hallucination in generating wiki bio entries. External Memory Augmented Neural Networks, MANs, have been proposed to enhance learning of long-term dependencies in input data, showing improved performance in various tasks. These models incorporate a trainable slot-based memory into a recurrent neural network, with an attention-based reading mechanism to compute a weighted average of memory contents. On the other hand, Conerva machine and its successors offer better performance in tasks like image reconstruction and generation compared to other models. However, this is the first study to investigate how these models can adapt to LLMs and aid in knowledge updating. Transformers face challenges in accessing and updating long-term memory, and efforts to extend input context length encounter difficulties in integrating model knowledge with external facts. Augmenting transformers with external memory and k-nearest neighbor, KNN, attention shows promise in enhancing language modeling by utilizing additional context, although controlling memory during decoding remains a challenge. Section Summary. In this section, we explore the generalization to long input context by utilizing a hierarchical memory model in Larimar, which allows for efficient processing of extended contexts. By incorporating a fixed-size latent memory with the decoder, Larimar enables truthful copying from context in a generalized manner, mitigating hallucination in wiki bio generation. The Jaccard index analysis reveals that for a specific range of chunk sizes, particularly around k equals 8, Larimar excels in reducing repeats and hallucinations, showcasing its potential for enhancing generative tasks. Section: Model Editing. In this section, we explore different approaches to editing models. Editing methods are typically divided into three main categories: the recognition phase, the association phase, and the mastery phase. In the recognition phase, the focus is on providing the right context to help the model output accurate information. This can be achieved through showing similar examples or training an external model on edits. The association phase involves merging new knowledge with the existing model, either by adding and training specific neurons or by incorporating an adapter that stores edit key value pairs. The mastery phase involves learning to update the model's own parameters, such as through regularized fine-tuning or hyper-network-based methods. Recent studies have also introduced the locate-then-edit approach, which involves tracing causality to identify relevant hidden states and updating corresponding weight parameters to directly incorporate new information. However, current model editing techniques face challenges such as high training costs and difficulty in adapting to new data. Updating large language models, LLMs, efficiently is particularly challenging due to the significant time and memory requirements involved. Additionally, the assumption that knowledge in LLMs is localized has been questioned, suggesting that simple parameter updates may not be sufficient for comprehensive edits. LLM performance can deteriorate with multiple edits, leading to issues like knowledge loss and distortion. While some propose using external cache or memory-based editing to avoid directly modifying the model, challenges remain in selectively forgetting outdated or sensitive information. Our approach introduces a novel method to enhance LLMs with generative memory, allowing for dynamic editing and adaptation without the need for retraining. Unlike traditional methods that update model parameters or use external memories, our approach does not require multiple demonstrations for control. Our method, Larimar, does not rely on negative examples for unlearning or necessitate tailored fine-tuning or additional layers. It complements in-context unlearning strategies, such as those used for forgetting specific facts.